Let's talk about the ideal gas law. There's actually four laws that preceded the gas law, and the gas law is sort of bringing them all together. So there was Boyle's law, which looked at how pressure varies with volume, and pressure is caused by the gas particles bouncing up against the side of the container. And so if we somehow shrunk it, and so I sort of imagine a balloon. So I have air in a balloon, I seal it off, and then I start pushing in on the balloon. There's less space for the particles inside. That means it doesn't take as long for them to hit one side and then bounce and hit the other side. And so therefore the pressure will increase as the volume decreases. There's Guillotine law, which shows how pressure is related to temperature, assuming that the volume is constant and we have the constant number of particles in it, or molecules more specifically. That as I increase the temperature, basically I'm increasing the kinetic energy of the particles inside of the gas molecules. The gas molecules with greater kinetic energy are moving faster, which means they're going to hit the sides more often, which means pressure increases. There's Charles' law, which relates the volume to the temperature, assuming pressure is constant and the number of molecules stays constant, which means as I increase the temperature, if I can change the volume, then what that's going to do is that's going to cause the whatever it is to expand. Imagine a hot air balloon. With a hot air balloon, as you increase the temperature, you're getting the particles moving around faster and they bounce up against the sides, causing the balloon to expand, because we are assuming pressure is constant. And the last one is Avogadro's law, which relates the volume to the number of particles. Assuming I keep pressure and temperature constant, as I increase the number of particles, then if I keep the volume the same, then the increase in number of particles means more particles will be hitting against the side of the container, which means greater pressure. So in order to keep the number of particles hitting the side to be the same, we have to increase the volume. Now, if I imagine, because of the relationship there, the fact that from Boyle's law, pressure is inversely proportional to volume, that means the pressure times volume is equal to some constant. In other words, as one goes up, the other goes down. Pressure and temperature are directly proportional, which means that the ratio of them is a constant, and volume to temperature, also directly proportional, is another constant. So if I multiply the left-hand sides here, so I multiply this times this times this, I got p squared, v squared over t squared, and that's just going to be equal to the product of whatever those constants are. So if I take the square root of both sides, I get pv over t, and on the right-hand side, I have the square root of a product of three constants, which is just a different constant. So pv is equal to a constant times the temperature. Since the number of particles in these laws here is constant, I'm just going to incorporate that as part of this constant right here. And I also know that volume and the number of particles are directly proportional, and so it works out to bring that in. And so I have a different constant times the number of particles. And we can now name that constant right there as the ideal gas constant, which has a value of that. There's different units for it, obviously, and therefore different numbers. So if you're looking at that and going, wait a second, that's not the number I saw before, just make sure the units are working. Are these the same units as you've seen before? So just doing a little quick plug and chug. Standard temperature and pressure, we established these. It actually did change in 1982. At least the standard pressure changed in 1982. And so you might have seen this value right here in some unit or another, but the 1.01325, sometimes in a different unit, 101.325. But currently standard pressure in international standard units, 10 to the 5th pascals. So what I want to do is figure out what would be the volume of a mole of gas. Again, I mentioned in another video, but if you're not familiar with a mole is just a number. If I said I had a dozen gas particles, you know I have 12. If I have a score number of gas particles, I've got 20. If I've got a mole of gas particles, I've got 6.02 times 10 to the 23rd molecules of gas. So solving for volume, it's just basically that divided by P. N is the number of moles, so 1 mole times the ideal gas constant times the temperature in absolute terms, divided by the pressure, and I end up with that number of cubic meters. If I did a conversion into liters, which is typically how the volume is seen, then I first got it into cubic centimeters, then into milliliters, then into liters, and I end up with that number right there is the number of liters in a mole of gas. Notice I didn't specify what kind of gas it is other than it's ideal. There it is. I'm just going to flash back one more thing on moles. That 6.02 times 10 to the 23rd, that's known as Avogadro's number, as is written right there. So if I take the number of molecules inside a container, divide by Avogadro's number, I get the number of moles. So mole is just an indication of how many particles there are.